Hello, party people. Welcome to the ChaosWest stage. The next talk is held by Tom Twiddlebit. The one or the other person may know Tom Twiddlebit. I think I just should hold the micro in there and then interesting things happened. So I will try to bridge the time shortly. This is a self-organized session. You can bring your papers and hold your project or kink that you have here on stage. We put it on the media CCC. You can show it around. So this stage is made for you basically, and it's so well off that we don't have we do have a few slots left. So thank you very much, community, everybody of you here to make this Congress so special, and add your personality to it too. So, Tom, Lynx, are you ready? You finished your discussions?
Okay.
Hallo?
Ich kann was?
Auf Deutsch oder auf Englisch eigentlich?
Englisch.
Ah, okay. So, please, dear audience, applause for Tom Twiddlebit and the fourth programming language.
Thank you very much. I hope that in half an hour you will give me a hand as well. I have always been in a minority position in the chaos environment because I'm a Force programmer since 1980. And I'm so happy with the language that I never felt any need to use something else for the things I'm doing. And I will relate to you why this is the case, and I will take a very unusual angle in that respect. Where it comes from, I mean, that is not controversial. It was developed by Charles Moore in the 1960s, and over a period of 10 years he experimented with different concepts. And it all started because he was programming an IBM 26 something using punched cards, of course, in the 1960s. And he had different, what we would now call subroutines. Every subroutine was a card deck. And he was looking for a mechanism to pass arguments from one card deck and the programs to the next card deck and the programs. And this is why he wound up with a data stack. So the first program was running, left its results on the data stack, and then the next card deck would pick up the parameters on the data stack and process them further. So that is one of the constituents of the Force programming language. Then after this period of 10 years, when he came to a version of his personal programming environment that in retrospect he called this then was Force. He used an assembler on some mini computer, I think it was a Varian, and he wanted to call it Force because this was a time when everybody was talking about the third generation of languages, and he wanted to leapfrog all of that. But then, unfortunately, the assembler only accepted 5-letter identifiers, and so the U had to go, and it became Force. The programming language is based on a conceptual model of a CPU, and this is basically the conceptual model. You have a data stack. You have the two top items of the data stack, which have a special role. If you think in hardware, they would be registers. The top of stack and the next of stack. And the top of stack and next of stack feed the ALU for binary arithmetic. I mean, with two arguments. And the result goes back into the top of stack. And then there is a return stack because we want to do subroutine calls and returns. And there is this little path on the left where you can exchange data between the return stack and the data stack, which comes in handy sometimes. I get into that later. And then, of course, the program counter is connected to the return stack. And why I wrote this arrow to the memory, I don't know. This is not necessary, but basically the data stack is also connected to the data memory, and you can store and retrieve results there. That is very conventional. What is unconventional, that instead of a register file, we just have a stack. And everybody of you who ever used the original Hewlett-Packard calculators knows how you do arithmetic on a stack. That is called postfix notation or postfix operation, and the data stack is the parameter storage used for evaluation of expressions. All operators and functions take their parameters from and leave the results on the stack. Fourth, words, and why they are called words, I will come to that in a minute. What you usually would call functions do not have parameter lists. So you don't need the opening paren and then this, that, comma, and another parameter, closing paren. No, they just use the stack as parameter exchange. And so, this is one of the drawbacks of force. You do not name the parameters. The parameters are just there, and the programmer has to take care that the parameters are really there in the order needed by the next word you call. Just to make an example, arithmetic operations, you put a 1 on the stack, you put a 2 on the stack, you do a plus, and then you put a 3 on the stack, and you multiply, and the dot is a print operator, and the result is 9. Because 1 plus 2 is 3, and 3 times 3 is 9. So this is exactly how the Hewlett-Packard calculators used to operate. Okay. Manipulating the stack. So the difference between a register-oriented machine and a stack-oriented machine is not as big as you might think. In both cases, you have the difficulty that your parameters that you need in order to call a function are not in the order that you need them. In a register machine, you have to exchange registers. On a stack machine, you have to reorder the parameters on the stack. And you have a couple of operations to do that. Let me explain this notation here between the parens. Before the dash dash, that's the number and semantics of the operator before the operation. Then comes the operation, and at the right side you see the result. So the dupe just duplicates an item on the stack. The drop throws away an item on the stack. The swap exchanges the two top items on the stack. And the rot goes down to the third operation parameter on the stack. And then the minus rot is exactly the opposite of the rot. Now you might start wondering, why is minus rot a valid name? Because most programming languages would say, aha, this is a minus followed by a rot. Not so in force. I will jump ahead here. Nah, this is too bad. I don't quite remember my presentation. Anyway, I keep in order. So this was the things happening on the data stack. Now we also have the second stack, the return stack. And the return stack is primarily used to store return addresses of a word, for a word or a function call. And it also serves as a storage location for loop indices, and therefore it is very easy in Force to nest loops. Because if you are inside a loop and you do a call, then automatically the old loop index gets pushed on the further down on the return stack, and then you can do your word, and the return automatically retrieves the loop index. And in addition, the return stack can be used as a temporary data storage to get some parameters out of the way which are currently not being used. The interpreter. Force is an interactive system that is controlled from the command line. So in that respect, it is similar to Python. It is very similar to Lisp, by the way, only that Lisp uses prefix notation and Force uses postfix notation. All words are kept in a linked list of word names associated with compiled code. Now this is what you conventionally would call the syntax tree. Although, because it is an interactive system, this syntax tree, or the dictionary as we call it in Force, is always present. And the way it operates, you type in a string of ASCII characters separated by a blank, and then the interpreter goes ahead and looks it up whether it can find the string in the dictionary. If it finds the string in the dictionary, then it jumps to the associated executable address. If it cannot find the string, it tries to convert it into a number according to the setting of the variable base. So if you have a 2 in the base, you work in binary. If you have a 10 there, it's decimal. If you have a 16, then you work in hexadecimal. If it is neither found in the dictionary nor converted into a number, you did a typo. And the system says, well, I don't know that. Defining new words. So how do you define new words? The basic operator is a colon, and then after the colon comes the name of the new word you are defining. And then usually you write a stack comment. So you say, what do I need before the word starts, and what is the stack situation when the word has finished? And so we could define a word 4 plus that just does a 4 plus intuitively. But of course you can do nasty things. Like for instance, you could define colon number 2 4 semicolon. And all of a sudden, if you now type in 2, there would be a 4 on the stack. So that is something you should not do, but it's possible. So 2 times, I think it's pretty much self-explanatory. You duplicate the n1 on the stack, and then you add these 2 copies of the same number together, and that is 2 times or a shift left. Just to give you an idea of how you program applications in Force, then look at, we have a washing machine. And so this is the washer, and the washer washes, it spins, it rinses, and then it spins again. And the Force compiler is just a one-pass compiler, and you do not have forward references. So if you want to make this definition, you first have to define wash, spin, rinse, and spin again. And just as an example, I mean, the definition of rinse could look like fill, agitate, and drain. And then the further you go down, the closer you come to the hardware, and then in the end, you will have nasty hexadecimal numbers that get stored in some addressable register. what makes Force so unique and why this is called an extensible language, the fact that newly defined words are exactly on the same level in terms of usability as the core word set we had to start with in the first place. So in a sense, you could say the Force programming language is the assembler of a virtual machine that you can extend. So you can increase the number of instructions that this virtual machine is able to execute. Memory and I/O. So we have the fetch operator that consumes an address and returns the content of the memory cell at that address. In Force, we have no notion of bytes. In Force, we have addressable cells, and the addressable cell may be more or less any bit width wide. I mean, conventionally, you have 16 bits, you have 32 bits. From an engineering point of view, 24 bits make much more sense than 32, for instance. And if you come to a Force engine implementation on an FPGA, then you will find that the internal program in FPGAs is not 8, it is 9 bits wide. And so it is very tempting to then just use an 18-bit machine, for instance. Perfectly feasible because it does, your word width does not have to be divisible by 8. And if you want to operate on bytes, you just store 1 byte at one memory location, and if it has more than 8 bits, well, you just throw away the extra bits. Then you need words to display your results. We already stumbled across dot. It just shows the number on the stack as a signed number. U dot shows the top stack item as an unsigned number, like in addresses. And type, for instance, takes an address and a length and prints this as a string. Primitive data types. Yeah, this is a definition of a constant. The constant consumes a number and you give it a name. A variable allocates one memory cell in memory. And so if we now that we defined zwei und Wert, you can do zwei Wert store. And then if you do a Wert fetch, you get a 2. To get more fancy, you can create a vector. So create my vector just creates a name for the next empty memory cell. And it doesn't do anything else. And then you say, okay, my vector should be 10 cells wide. And so you do this with the ampersand stands for decimal. Decimal 10 cells a lot, and that gives you a vector then. The full line gives you a vector of 10 elements. And my vector, as I said, returns the address of the first element. And then you can do address computation in order to get what you want, or you can get more fancy, like defining a new data type. You can say, I want to define a vector of a limited size, and I want to be able to access the elements in the vector by passing the index to the name of the vector. This is difficult to explain, I must confess, because here we have a word where we defined the operation in 2 different time instances. So the code between colon vector, which enters the name vector into the dictionary. And when vector will be executed later on, it will create n cells and allocate them. So in this example, 10 vector indexed vector will automatically create a vector called index vector with 10 elements. And when we later on execute indexed vector, then the code between the does and the semicolon will be executed. And that means at the beginning we have an index on the stack, and in the end we have the actual physical address of the data item of that index location on the stack. There is a little bit of invisible mystery here, because the word does returns the address of the first location of the data type. So we have an index on the stack. If you execute does, we have also on top of the index, we have the address of the first field. Now then we first have to swap these two items to get the index on top. We apply the cells operator to it. I have to get to the cells operator, why the cells operator is needed. When Force is working on, let's say, an Intel machine, then of course we do have bytes. And so if our addressable cell is 32 bits wide, it consumes 4 bytes. And the cells operator is exactly the operator that computes out of the number of the 32-bit item that I want, it computes the byte address on an Intel machine for it. And so we multiply the index, for instance, using cells by 4, because we have a 32-bit 4 system. And then we add it at this to the first address that was left by the does. And that gives us then the physical location of the data item at index in the vector. So 3 indexed vectors returns the memory address of the 4th element of indexed vector. And this is because Force starts counting from 0. So you always count 0, 1, 2, 3, and so on. Control structures. Of course, we have control structures and can modify the program flow as in every other complete programming language. Again, with a special feature that this is a reverse Polish notation. So we first compute arguments, and then we apply the operator to it. In this case, if we have the if clause, then we first compute a flag, however complex that might be, and then the if interprets the top item on the stack as the flag, and if the flag is true, the code between if and then will be executed, and if the flag on top of the stack is 0, then a jump after then is performed. So then if else then is also then easy, more or less easy to understand, although the syntax is unconventional. If the flag is true, we execute the code between if and else. If it is false, we execute the code between else and then. Another loop is the begin until loop, which always executes the loop at least once. And then at the end, we decide whether we jump back or whether we leave the do loop. And the other variant is where we compute a flag. If the flag is true, we execute something between while and repeat, and then the repeat jumps back to the begin, does the next computation, and only if we are false, we jump out of the loop after the repeat.
Another variant is counted loops that
consume 2 items on the stack, a start value and a limiting value, and then with do loop, we loop so many times around, and then there is the I which returns us the current loop index. Compiler extension. Now things become really interesting, because not only can you define new words or functions in Force, but you can also modify the compiler itself. And modifying the compiler, the important name here or word here is the word immediate. That is attached to a word definition, and it just means if the compiler encounters an immediate word, that will be immediately executed by the compiler. Whereas any word that is not immediate and that is part of a word definition, its executable address will just be compiled into memory and nothing else. And so in essence, this if and this then and this if else then, they are all immediate words which execute while the compiler is working. So this mechanism, extension of the compiler, can be used to bake your own case or to bake your own struct compiler, or, I mean, to make it really interesting, I call this syntactic sugar. So the question at hand was to define a Morse alphabet generator. So you would type in numbers and strings, and it would be converted into the Morse code. And if you sugar syntactically your compiler, you can write it down in this syntax, which is pretty intuitive. You have a dot and a dash, and then you have the vertical bar, and the vertical bar then takes a name, and the name from this moment on will be associated with the dot dash. So what you have to do in order to do this magic, you have to define Morse table colon as the beginning of the definition, semicolon Morse table as the end. Of course, there were more lines, they don't fit here. And so basically what you have to do is you have to define your compiling words, Morse table colon, semicolon Morse table, vertical bar, which is used at the end of the dots and dashes. You have to define your dot and your dash. And each of those definitions takes between 1 and 4 lines of code. And if you are an experienced Force programmer, I mean, you look at the problem and then it is very easy to come up with a solution to do that. This pretty much covers the basic capabilities of Force. It is standardized, and there are annual meetings on a European, or actually nowadays on an international level, the Euroforce conferences, and this is where the standardization and ongoing standardization process is taking place. Unfortunately, I'm missing one important slide here. Okay. I will use this for explaining. Why I love Force. I didn't tell you why I love Force yet. I love Force because any character except tab and space can be part of a name. So I can use all special characters in a name, and this is the mystery why in Force minus rod is not a minus and a rod, it is just the word minus rod. And for, I mean, pretty obvious reasons, it is the inverse of rod, and so it is usually called minus rod as an indication of inverse. And that means, in essence, the hundreds of days that up to now went into regular expression compilers. Force doesn't need regular expressions. I mean, the parsing process is so simple, you just look for the next space, and that's all. And everything that is enclosed in space, or to be more precise, is enclosed by white space, is just a force word that gets looked up in a dictionary. If that is not successful, an attempt is made to convert it to a number, and that's all. Which means that, or to put it in another way, when I started to program in force, I used to study computer science, which was pretty new in the mid-1970s. And I stood in awe before the compiler writers, because that seems like an extremely complex thing to do. And when I then started to program in force, and when I learned how to extend the compiling capabilities of force, this awe of the compiler writers went completely away. It is simple. And if you think about how force works and how you program in force, it is basically pure anarchy. Because you can, if you are a good programmer, you can do excellent things in force. If you are a bad programmer, you are able to write the most gibberish code, which is absolutely unrememberable in no time. So in a sense, force is a programming amplifier. It gives you capabilities that you don't have in most other programming languages to express yourself and to create your own syntax to solve a problem. And then the next logical step, of course, is because the force virtual machine is so simple. On most register machines, it has to be emulated. I mean, just like Java has to be emulated. And there are also bytecode implementations of force, like, for instance, OpenBoot is just a bytecode implementation of the force language on a large variety of different processes. And the advantage of this approach is that if you have peripheral I/O cards, they will execute the force bytecode. And then the force bytecode is just interpreted on these different processes, but the bytecode on the peripheral card remains exactly the same on all machines. So this is where the big market niche was for OpenBoot, when we had at least 4 different variants of RISC processors in the 1990s. But since the force machine the virtual machine is such a simple thing, it is very easy to implement it in real hardware. And I have been doing that for the past 15 years. And because I earn my money by filling FPGAs with content. And so if I have a new piece of hardware with an FPGA on it, the first thing I do is I put microcore on it, and then I can also always explore the FPGA from inside. And I can program the FPGA, explore it, and changing the code and executing it on the FPGA on the software level takes, 10-15 seconds, whereas to run a new version with a changed FPGA, with a changed VHDL code on the current generation that I'm working on, which is for satellites and radiation environments, you were talking about 45 minutes. So this approach makes a lot of sense. And if you look at the diagram, you see the one-to-one relation more or less to the virtual machine. And then, well, this is not really part of the fourth talk, but this is my baby, basically. Apart from interrupts, since I'm a real-time programmer, interrupts are very important. There is also the flip side of the coin. And the flip side of the coin is, and I spelled it out, an interrupt is an event did happen that was not expected by the software. Whereas the pause exactly the opposite. An event did not happen that the software expected. Like the software wants to fetch a byte from a UART, but there is nothing on the UART yet. It's still to come. And in microcore, I converted this to like the flip side as a hardware signal, as a flip side to the interrupt. And then what you basically do is the hardware signals on a hardware level that, well, this operation cannot be done. Then a trap is called and calls the scheduler and does some other task in the multitasking environment. Okay, that's the end of the talk. These are interesting links in that respect. Questions, please.
Questions?
So how many lookup tables do you need for your fourth machine?
Lookup tables? Why would I need lookup tables?
No, in the FPGA, just the size of the resource.
So, okay. I have been working on the micro-semi, what used to be Actel, for such a long time. They have a very, very fine granularity. So on those, it is around 5,000 cells. I think if we talk about Xilinx or Lattice or Atmel, we are talking about 2,000 to 2,500.
Any more questions? I have a question. You're here with We Fixed the Internet guys, is that correct?
Yeah.
What has the program language fourth to do with We Fixed the Internet?
Ask Bernd. He did a full new internet stack, all programmed in Force.
Yes, he had the talk earlier today, and he said, and he referenced yours. So maybe Bernd, for the others, just compress it.
One problem we have with the internet is the attack surface. It's just too complicated. Everything we do is too complicated. So we built a huge attack surface for all the evil people out there. And we have to go down, make it simpler and simpler until we understand what we are doing. And Force is one way to make things simpler, at least our development systems. That is the point here. And it's not just writing a stack in Force, it's also, when we think about JavaScript, it's too complicated. Even our image file formats are now so complicated that you can inject attacks in a PNG or a JPEG. And that's not the right way. So we have to cut down all this complicated and things, and the complicated stuff is just the accidental complication. It's not necessary complication. And Force teaches you how to be simple. It's a state of mind. Solve simple. Don't solve complex things.
Thank you very much.
maybe a dumb question, but when you run this fourth program on the FPGA, how can I imagine this? Do you upload byte sequence to this FPGA? For it, or?
Yeah, I have a little what is called. I don't remember it from the Spark architecture. So you have something on the side with a receive and a transmit channel that allows you to connect it, as we call it, the umbilical, to a host computer. And the host computer runs a cross compiler, and a full image of the program and data memory on the target system. And with this technique, you are in complete control of the target system, because you can compile code that you have written in an editor, you load the file, and you compile for the target system, and that compiles it into a memory area in the host. And then you transfer this memory image into the target system, and then you start the target system and let it execute some executable routine on the target system. And then, I mean, this is standard technology, basically, how you connect a host and a target system, your umbilical, and then you have a very simple monitor loop that waits on the umbilical to receive an address that it should jump to. And once it has executed what it found at this address, then if everything went okay, it sends back a 0. So the host system knows then, well, this word has been executed and everything was fine. And if it is not a 0, then it is either a warning or an error. That's simple. Did this answer your question?
Not really. I will come to you.
Thank you. Any more questions from the audience?
Okay, thank you very much
Tom.
for your attention.
Vielen Dank.